Hello, my name is Michelle, and today I'm going to be talking to you about stars and the star life cycle. In this presentation, students will learn what stars are and the life cycle of a star depending on its size. The target age group for this lesson is 6th grade and up, and students will learn how to identify the stage of a star and what its next stages will be. So what are stars? Stars are spheres of gas held together by gravity. The history and evolution of the galaxy can be traced using the composition, age, and distribution of stars. Stars receive energy from the nuclear fusion of hydrogen to helium in the interior. There are 3 layers of a star's interior. The first is the core, which is the innermost region of a star. All of a star's energy comes from here because this is where nuclear fusion occurs. The radiation zone is where energy from the core travels in the form of electromagnetic radiation. And the third layer is the convection zone. Here, energy moves through convection currents, the same way energy would move in a pot of boiling water. There are also 3 layers of a star's atmosphere. The photosphere is a very thin layer that emits most of a star's light. The chromosphere can be seen during an eclipse. This middlemost layer has a pinkish red color. And the third layer is the corona. This is the outermost layer of a star that is also visible during an eclipse. It is nicknamed the crown of a star. Here are 2 diagrams showing the different layers of a star. In both diagrams, you can see the innermost layers and the 3 atmospheric layers of a star. Here's a diagram showing the life cycle of a star. All stars start off as stellar nebula, but then the life cycle of a star changes depending on its size. Very big stars will end up being either neutron stars or black holes, while medium-sized and smaller-sized stars will end up being white dwarfs. Nebula are clouds of dust that collapse to form a protostar that will one day be a star. As the cloud collapses, the material in the center heats up. Any remaining dust can become planets, asteroids, comets, or remain as dust. And then here you can see 2 pictures of different nebula in the universe. There are 4 types of nebula. The first is an emission nebula. A star energizes the atoms in the cloud with UV radiation, causing the nebula to emit light in different colors. An example of an emission nebula is the Tulip Nebula, which you can see a picture of right here. Reflection nebulas are those that do not emit radiation on its own. It reflects light energy from a nearby star. Messier 78 is an example of a reflection nebula. Dark nebulas block the light from objects behind it. The Horsehead Nebula is an example of a dark nebula. And finally, planetary nebulas are a type of emission nebula in which the source of energy is a hot white dwarf. The Ring Nebula is an example of this type of nebula. The Tarantula Nebula is a specific type of nebula in the universe. It is one of the largest nebulas, stretching 600 light years and containing over 800,000 stars and protostars. It has glowing filaments of dust that resemble the legs of a spider, which is why it has the name Tarantula Nebula. The region is heated up to millions of degrees because the massive stars within the nebula blast away material and produce intense radiation and strong stellar winds. The next thing we are going to talk about is main sequence stars. A main sequence star is any star that has a stable balance of pressure, of outward pressure from core nuclear fusion and gravitational forces pushing inward. About 90% of the stars in the universe, including our sun, are main sequence stars. A higher mass main sequence star will not live long because it will burn through its material faster due to higher temperatures in its core. The term main sequence comes from the Hertzsprung-Russell diagram, which can be seen here. In this diagram, the temperature of main sequence stars is related to brightness. Also, if you look at this diagram, it shows you how a star's temperature affects the color that it is. So the hotter a star is, it will be more of a blue color, but cooler stars are more of a red color. The Sun accounts for 99.89% of the mass of our solar system, and it's an example of a main sequence star. Over 1 million Earths can fit inside the Sun, but our Sun is not even that big when you think of stars such as UY Scuti, which is 1,700 times larger than our Sun. In the far future, the Sun will expand and engulf Mercury, Venus, and Earth as it becomes a red giant. This leads us into our next topic, which is red giants. When a star exhausts its hydrogen fuel source, the star starts to collapse. Before it collapses too far, the contraction heats up a shell of hydrogen around the core. This, along with the higher temperatures, creates a new pressure that pushes out the star's outer layers and makes it a red giant. Larger stars will become supergiants. The formation of red supergiants is similar to that of red giants. The star gets bigger and bigger until it has fused elements up until iron. A red supergiant happens only to stars that are more than 10 solar masses, or 10 times the size of the Sun. Red supergiants only last up to 1 million years and fuse heavier elements during this time. Gamma Crucis is a red giant, and it is the 25th brightest star in the sky, and it is the closest red giant to Earth at about 88 light-years away. It is in the southern sky, so it cannot be seen from the northern hemisphere. Betelgeuse is a red supergiant, and it is the 10th brightest star in the sky, and it is 640 light-years away from Earth. It is part of the constellation Orion. Now we are going to discuss supernova. Once a red giant has fused elements up to iron, the core succumbs to gravity and collapses, causing an explosion called a supernova. Supernovas can shine as bright as an entire galaxy for short amounts of time. Keep in mind that supernova can only happen to very large stars. Neutron stars are made from the leftover material from a supernova, and they are extremely dense. If the core is less than 4 times the mass of the Sun, it becomes a neutron star. Although they are only a few kilometers in diameter, neutron stars are more massive than the Sun, and they are made almost entirely of neutrons. Very large stars, after they go through a supernova, can either become a neutron star, or if they have a bit of a larger core, they become black holes. If the core is more than 5 times the mass of the Sun, it will collapse into a black hole. Black holes are so dense that nothing, not even light, can escape their gravity. Black holes are identified by looking at the effect on objects around it and radiation that leaks out of its edges. Since not even light can escape a black hole, they are in a way invisible, which is why researchers have to look at how objects surrounding a black hole are affected. Recently, one of the first pictures of a black hole was ever taken, and that image is shown here. So now we've discussed what happens to very large stars in the later parts of their lives. But what about stars that are medium-sized or smaller-sized, like our Sun? Well, these types of stars become white dwarfs. A red giant star will stop fusion completely once it burns up all the helium in its core. The star will shed its outer layers into a planetary nebula, and gravity collapses the star's core to a white glowing object about the size of the Earth that will eventually fade out. Right now, only 8 known white dwarfs exist in the 100 star systems close to us, but eventually 97% of all Milky Way stars will become white dwarfs, which means that a majority of the stars within our Milky Way galaxy are medium-sized or smaller sized. Here are some additional links to some videos that go into more depth about the topics discussed in this video, and some links to some practice questions. Here are links to websites that were used to find the information within this video. Hello, my name is Michelle Serbin. I love doing all sorts of activities such as playing piano and doing research, and I hope this video helped you out.